Yes, in last time's lecture, we discussed about the biasing of a bipolar junction transistor and how to bias it to get into what we call the active mode. So we are looking at bipolar junction transistors, or what we call semiconductor transistors. I'll just take you through the key points about the transistor. Before that, we discussed about the working of the PN junction in forward bias and reverse bias, and thereby how a PN junction can be used as a diode in an electrical circuit. Then we looked at the working of it as a transistor, where a transistor is a three-pole device, like we saw. It consists of a in-between portion, which is called the base, which is sandwiched by the two other parts, which is the emitter and the collector. Now, in the case of semiconductor devices, basically the base, emitter, and collector are impure or extrinsic semiconductors, which are either positive and positive type for emitter and collector, sandwiching a negative type for the base. So this is called a PNP, bipolar junction transistor, or it can be two N-type semiconductors, which are on either side of a P-type semiconductor, in which case it is called a NPN type bipolar junction transistor. So again, suppose this is the emitter, base, and collector pin. So this is the N-type semiconductor, this is the P-type semiconductor, and N-type. So again, this becomes the what we call the NPN bipolar junction transistor. So in a circuit diagram, what we had seen is that these are represented by these kind of symbols, where the base pin is always the one which is with respect to the thicker kind of rod, and the emitter and collector pins are like this. For example, if this is a PNP, then the arrow will point from the emitter to the base, because the base is the P type, is the N type. So that will look like this. So this is an example of where this is the emitter pin, this is the base pin, and this is the collector pin. Now this is what we call the this is the PNP type of transistor, because the emitter will be P type. So the arrow always points in the forward biasing of the base emitter junction. So if the base emitter junction is forward biased, you can see the arrow will point from P to N side. So from emitter to base means the emitter is P type and the base is N types. Whereas if we have an NPN like over here, in an NPN type, the base is the P type semiconductor. So the forward biasing of the base emitter junction has to point from base towards emitter. So the pin connected to the arrow is called the emitter pin. The pin connected to the thicker rod is called the base pin. And the third one is the collector pin. Now the arrow's sense or direction always gives us the direction of forward biasing of the base emitter junction. So forward biasing of the base emitter junction in this case would mean that this is a NPN transistor. In the case of the first one, would mean that it is a PNP transistor. So this is the circuit symbol. Now we had also seen, as far as the the device itself looks, it's somewhat a little bit different. So we had seen that a typical old style, what we call the circuit board type of PNP transistor or NPN transistor, not the integrated circuit board type. In the integrated circuit board, what happens is that you have like a silicon sheet or a layer of silicon on a substrate material, and all the devices are literally etched onto that silicon sheet. So it's not like you have separate resistors, diodes, capacitors, inductors, etc. You just have all the different circuit elements, especially the semiconductor elements like the transistors and the diodes, which are directly, you can say, drawn on the silicon wafer or etched onto the silicon wafer. Okay, but those are modern day integrated circuit chips or VLSI circuit chips, large scale integration chips, etc. The type you would see in computer hardware, etc. But if you look at the basic electrical circuit kind of situation, where you have a circuit board and all that, and you have the individual circuit elements like resistors, capacitors, and along with the transistors, you see that transistors, that small cylindrical kind of small aluminium cylindrical kind of shape that you have with 3 pins coming out of it, base, emitter and collector. So for that type of typical transistor, the circuit, the device design is something like this. You have like a narrow in radius but large in length kind of cylinder, which is in contact with a very comparatively thinner cylinder like this, which is in contact with comparatively medium thickness cylinder but of much larger base radius, that kind of thing. So this is your emitter pin. This middle material, the cylinder in the middle is the base, and this is the collector. And so conducting wires connecting here as the emitter, base and collector. So what we'll see in the physical form factor. So the important points in the physical form is that the base is narrow in width, whereas also the base emitter junction has lower contact area, whereas the collector base junction has comparatively large contact area. So this is as far as the physical dimensions is concerned. You also have that the emitter has high concentration of dopant. So that means it has large concentration of charge carriers. In fact, that is why it is called the emitter, because it is the charge carriers that the emitter sends into or diffuses into the base that contributes to the most of the current that passes in the transistor, whereas the base has low concentration of dopant. So correspondingly, it has low concentration of charge carriers. And the collector, this one has moderate dopant concentration. So this is what we talked about last time, the important design features or the features of the form factor, including the dimensional size as well as the type of materials used for the semiconductor device or for the transistor. Just a moment. Okay, so back to the concept of biasing. So what we have seen is that there are various types of biasing, but what we are interested in here is the biasing for bringing the transistor into what is called the active mode. Okay, so in active mode biasing, what we do is two DC voltage cells or batteries are used to bias such that, so this is very important, base emitter junction is forward biased and collector base junction is reverse biased. So for example, if we have a transistor which is a, let us say, PNP type of transistor. So PNP means that the arrow would point from base to emitter. So it's pointing, as I have shown, from the base pin towards the emitter. The arrow is pointing in this direction. So you can see this is a NPN. My mistake. The arrow is pointing from base to emitter. That means the base is the P type. So this is an NPN type bipolar junction transistor. So if this was connected such that, or it is biased in the active mode, then the base emitter junction has to be forward biased. That means the base pin has to be given a positive potential compared to the collector pin, compared to the emitter pin, and the collector base junction has to be reverse biased. So that means the collector has to be given a higher potential compared to the base pin. Okay? So that is achieved by doing this kind of connection. That first of all, we ground the emitter, and then we connect the positive pole of a battery to the base, when the negative pole is connected to the ground pin, so that this battery now achieves the first task, which was forward biasing of the base emitter junction. Now so the emitter is at zero potential because it's grounded. The base is at the potential of whatever the EMF of this battery is, right? And the collector has to be even higher in potential, because remember, collector base junction has to be reverse biased. Okay? So to achieve that, we connect another battery of higher voltage, like this over. So you can see that the emitter pin is at zero potential because it is grounded. The base pin is at a potential of, in this case, plus VB, right? So this is ensuring that the base emitter junction is forward biased. Because remember, here we are talking about a NPN type bipolar junction transistor. The base is the one which is the P type. Now the collector pin is at a potential of VCC. So as long as VCC is greater than VBB, okay, that means the collector base junction is reverse biased. That is, the N side is at higher potential. Collector is the N side, because again it's the NPN, remember. It's the NPN bipolar junction transistor. So that being the case. So the two cells here have achieved this purpose. Okay? So just make a quick review of this part and make sure that you understand the role played by the two DC batteries here in achieving these two tasks: base emitter junctions forward bias and collector base junctions reverse bias. Then we will also discuss for the other type of transistor, which is the PNP. This is for the NPN. Alright, so this part is clear. So similarly, if we were using the PNP transistor, then the biasing would be done in this way. So common emitter configuration, as I told you, means that the emitter is grounded. Whichever thing is grounded, that is called the common pin. So here the emitter is the pin which is grounded, but only this time we are dealing with the PNP. So the emitter is in fact the N-type semiconductor. This arrow here looks like this, and the base is the P-type semiconductor. Collector, base, which is the N-type semiconductor, and emitter, which is the P-type semiconductor. So the fact that first of all I am dealing with common emitter configuration. So common emitter configuration means the emitter pin has to be grounded. Then the next thing is I need to forward bias the collector. Sorry, the emitter base junction has to be forward biased. So that means the base pin, which is now the P-type semiconductor. Remember, this was, we are dealing with this. Okay, so remember the arrow always points from positive to negative. So the emitter pin is the P-type and the base pin is the N-type. So this has to be forward biased, means the biasing has to be like this. The DC battery here will make sure that the voltage of the emitter, when that is 0, the voltage of the base pin is now minus of VB. So that ensures that the base emitter junction is forward biased. So this time it is the emitter which is the P-type semiconductor and the base which is the N-type semiconductor. Okay. And similarly on the other side, the collector base junction has to be reverse biased. So the collector is now the P-type, remember, and this is the N-type. So reverse bias means collector has to be at lower potential than the base. So that means you will connect another battery like this, so that this is what is happening. Now the voltage of the collector pin is minus of VCC, whereas the voltage of the base pin is minus VB. So as long as the voltage of the collector pin is lower than the voltage of the base pin, what does that mean? The collector base junction is in reverse bias. So this is again the same thing, but only instead of using a PNP transistor, or rather instead of using an NPN transistor last time, here we are using a PNP transistor. So the biasing is done just with the two cells exactly opposite polarity compared to when we had seen an NPN transistor. If you compare this diagram with the diagram above, the polarity of the two poles is just, two batteries is just reversed. Rest everything is the same. Common emitter configuration for active mode. Below also we have the same thing, common emitter configuration. But just because there it was NPN and in this diagram, the one below now, it is PNP. So the polarities are reversed. Now once this happens, once we connect this way, so biasing results in DC currents, which we generally denote by the emitter current, base current. and collector current such that, so let's take one of the two circuits above and understand how the currents are flowing now. Let's take the first one, NPN. Pardon, this one is the collector pin. So once we've achieved the biasing, so remember this is a NPN type. So this side, the base side has to be at higher potential. So the polarity of this DC source will be like this. So that the base is at higher potential than the ground pin. And on the other side, the collector is at even higher potential because the collector's potential has to be larger than the base's potential. That is reversed by this forward bias. So what happens here is that the base emitter junction it is forward biased. Okay. So there is a strong diffusion. Remember, in forward biasing of any PN junction, it's the diffusion current that dominates. So large amount of, so typically here it's an NPN. So remember the emitter will be rich in free electrons because it is heavily doped. So there's a rush of free electrons which are going into the base, and that contributes to the current across the base emitter junction, which we call the emitter current. Okay. So electrons are actually going in this direction from emitter to base. So conventional current is going in the opposite direction from base to emitter. So that is your emitter current. Okay. Now out of the electrons that diffuse into the base, most of them also migrate to the to the collector. Now why that happens is that the base itself is narrow in width. So by virtue of momentum, most of the charge carriers which are migrating or diffusing across from emitter into base actually naturally manage to also drift into the collector. And secondly, the collector base junction is also pretty large in surface area, and plus it is reverse bias. So what happens is that this forward bias current, the strong diffusion current, which is basically the emitter current. So this emitter current mostly it converts into collector current. So the large majority of charge carriers that diffuse across the base emitter junction also manage to drift across the collector base junction. And to aid that process, you have three things. The base is narrow in width. That also allows this thing to happen. Secondly, the collector base junction, it is reverse biased. So it will allow this process to happen. That is, drift will be enhanced. And third, the area of contact, the contact area for the collector base junction is high, which we had seen earlier as part of the design criteria. So these three factors contribute to the fact that there is an IC which is almost equal to IT. That is, in this particular diagram, most of the free electrons able to diffuse from the emitter into the base. They would naturally find their way into the collector and contribute to this current, which electrons going in this direction means current is in the opposite direction, conventional current. So that is the collector current. So the collector current is almost equal to but less. So typically collector current might be approximately something like 0.8 to 0.96 or whatever times the emitter current. Slightly lesser but almost equal. and of course a small minority of charge carriers recirculate through this battery from the base pin. I'll explain. So in the above diagram, out of every 1,000 electrons which are diffusing into the base, maybe 990 something are going into the collector. They are drifting into the collector, contributing to the collector current IC. But a few of them, the very small percentage that don't manage to drift across the collector base junction, what happens to them? They get recirculated through this. So electrons going in this direction means conventional current is in the opposite direction, and that is your base current. Okay. So this flow of charge carriers contributes to what we call the base current, and the base current is a very small factor of the emitter. So by using conservation of charge, we see that the emitter current is actually the sum of the base current plus the collector current. But in this sum, IC is almost equal to IE, whereas IB is a lot less compared to IE. And that is where the alpha beta parameters come in. So such that we see that the collector current is equal to some parameter beta times the base current, where beta is typically in the region of 50 to 200 for standard commercial transistors. As you can see, base current is lot lesser compared to emitter current, so also lot lesser compared to collector current. So base current is basically collector current upon beta, where beta is a very large number, like 50 to 200. So whereas also we have the relation that IC is equal to alpha times IE, where alpha is typically something in the region of 0.9 to 0.96, something like that. Okay. So collector current is very close to emitter current, but slightly less. So these become the two important parameters. Okay. So this alpha beta parameters are actually nothing but a function of the design of the transistor. That is, what kind of materials are used for the individual base emitter collector, what kind of concentration they have for the dopant, and also what values of voltage we are using for the biasing. So any commercial transistor will come with a sort of rated value of alpha and beta, such that if you connect to the correct DC voltages which the circuit has been designed for, or which the transistor has been designed for, then it immediately achieves these ratios which are given by alpha and beta. Also note from here you have another relation between these. Now, from below you can see IE is equal to IC by alpha. So IC by alpha is equal to IB, okay, which we can write as IC upon beta plus IC. If you solve this relation, then you have something like this. You have this relation that there is a relationship between the alpha beta parameters. That relationship comes from this. Okay, this is coming from the fact that IE is equal to IC plus IB. So next step is this. Next step, when you solve this from this plus 1. Oh, my mistake. This is the inverse. This is actually 1 by beta. 1 by beta is equal to 1, or beta is equal to alpha. This is the relation between the alpha beta parameters. Okay, so this is again something important at board level and all. Or you can get a simple numerical question in JEE mains also based on this. Remember, this topic is exclusively for JEE mains. Semiconductors, logic gates, transistor circuits and all are not part of your JEE advanced syllabus. Okay. So now once we understand this, next we look at how we can make this transistor act like a amplifier. Okay. So bipolar junction transistor. In active mode biasing. As an amplifier. So what does an amplifier do? Let us understand that first. So what does an amplifier do? Any amplification circuit or amplification device it takes an input signal so this is the input and gives an output such that the output is amplified. So for example, if the input voltage is a voltage which is like this, it's like a sine wave, let's say. There's some amplitude V1 sine omega t plus phi. So what will happen that it will give the output on the other side as something having much larger amplitude. So uniform amplitude. Much larger. So this one has an amplitude V2, let's say, but it will have the same frequency. So V2 upon V1 will become what we call the voltage gain factor for the amplifier. Okay. It is the ratio of peak values of output voltage to input voltage. So just make a note of this concept of voltage gain and in general what an amplifier does. Then we'll discuss more. Okay, similarly, we also define something called current gain. If the input current is some amplitude into sine omega t like this, and the output current is like this, then the ratio of the amplitude of the output current to the input current, this becomes what we call the current gain factor. So typically in amplifiers in electronics, we talk about voltage gain and current gain, and that is what these two mean. That the amplifier circuit consists of an input side and an output side, where your input device is connected between two pins, which are called the input pins, and the output device is connected between two pins, which are called the output side of the amplifier. So whatever current is going into the amplifier through the input device is called the input current, and whatever current is extracted out of it through the output device is called the output current. So in a typical circuit, you will say that your amplifier, if it is this device, then on the input side, you're sending in some current by connecting something across this. So this is the input side of the amplifier. And this is the output side. So let's say you have connected some signal over here, which is sending a current I input, and the voltage across these two pins is the V input. And you connected some device here which is experiencing the output current. So it's like the load resistor or the load of the circuit, and the voltage across the load is becoming the output voltage. Whatever voltage you're measuring across this, that is becoming the output voltage. So the ratio of the output amplitude to the input amplitude in general is called the gain factor. Okay. Now if you're talking about current amplitude factor, or the ratio of the current amplitude of output to input, then that is called the current gain. If you're talking about the voltage amplitude of the output is to the voltage amplitude of the input, it is called the voltage gain factor. So now let us see how the transistor functions as an amplifier. So the whole functioning is based on that simple principle that when biased in active mode, okay, we have this relationship where IC and IB are DC currents. So there's no question of gain yet because there is no amplitude involved. But beta is a large factor, which is anything from 50 to about 200. So using this, we'll be able to achieve that gain. So what we do is see your regular kind of circuit. So emitter pin is grounded, common emitter configuration. The base pin is being connected using this DC source so that it is forward biased. The base emitter junction is forward biased, and the collector junction is the collector base junction rather is reverse biased. using this. Now, because of this biasing, what the circuit is achieving is that this current coming in here and this current coming in here, they are combining to give you a current IE here. But more importantly, IC is equal to beta times IB, where beta is a large factor between 50 and 200. So taking advantage of this, we can do this, that here, if we just modify the circuit now by connecting some appropriate resistance first of all here, and also connecting some kind of input voltage source over here. So between this and this, now we connect. So let me show the modifications with different color. So the first modification is that we've connected an input source over here. Okay. And we have connected some kind of input resistance which can be controlled or which can be connected such that it gives us some advantage. It gives us some parameters of what we expect. Whereas here on this side, across the collector emitter junction, we connect the load resistance. This is the load for the circuit. So whatever voltage is across the load resistance, that becomes our output. So this becomes our output terminal, and this becomes our input terminal. So now what happens is, as a result of, so that V input is a small amplitude alternating voltage, which we will consider as our input signal. It's our input voltage signal. So for example, it could be the voltage output of a microphone or from an antenna which receives and then sends as an input to the amplifier its signal. Whereas V output is the large amplitude voltage developed across the load resistor. So this is my terminology. So just pay attention to the diagram versus the terminology below, and then we'll understand how practically we achieve the gain, the voltage gain and current. So what happens is, the moment I connect this input voltage, this current changes from a DC to an alternating current. IB becomes like this. This current changes from a DC to an alternating current. So I'll write it with small. Okay. So on connecting V input, okay, across the base emitter junction, as you can see, what happens is that the base current becomes a non-DC value. So it changes to IB. Whereas, so that's why we use the small letter for current, whereas capital letter earlier was used for DC voltage. Okay. So just to illustrate this point, let me show you here next. What is happening is, because of that small signal input that we are connecting, before connecting, if you measured the current going through the base junction, you measured the current going through the base junction versus time, it would have been a flat line like this, because it's a DC current. So this is the DC voltage, sorry, the DC current through the base B, when no alternating source or input voltage source was connected. But as opposed to this now, what will happen is when I connect that voltage, that will make the net voltage across the base emitter junction vary, because that, so when V input equal to some amplitude V1 sine omega t is connected across the base emitter junction, as an input. What happens is that the current now changes to a time varying current. It's no longer a DC. So what would have been my flatline DC earlier, but now the voltage across the base emitter junction is still always forward biased because your DC battery is in place and it's keeping it forward biased. But the value of that voltage is now fluctuating because of the input voltage. So let's say you've connected the DC battery VVV of few volts. So in the case of no input signal connected, it would have kept the voltage across the base emitter junction a constant value of few volts. So the current going through the base would have been a constant flatline base current or the DC current. But now that input voltage is, let's say, a few millivolts in amplitude, but it is alternating. So what happens? The net voltage across the base emitter junction is fluctuating. It's not going between minus and plus. Understand this? What is happening now is across the base emitter junction, the biasing is not changing, because क्या होगा कि even though इसका polarity alternate कर रहा है, this one's polarity is alternating between plus minus and minus plus, but its amplitude is very small compared to this voltage. So always this guy is dominating. So it's always in forward bias. So there's always a current flowing like this, but the amount of current flowing will start fluctuating a little bit with a certain frequency, because now there is some input voltage, even though small in value, but it is making the net voltage across the base emitter junction fluctuate. So the current across the base emitter junction, or the IB value, now becomes as if it is fluctuating like this. Okay. And whatever amplitude this current has, that is called the input current amplitude. So this peak to peak value, it is 2 times the amplitude of the input current. So that is the input side of the circuit. So we call that as the Vin. So it's 2 times Vin. Okay. So this peak to peak value over here is nothing but 2 times Vin. So V input here is the amplitude of IB. Now, IB is actually the input current. So IB is not varying between plus of Vin and minus of Vin. It's not varying over here. It's always remaining positive, but its value is fluctuating. So वो fluctuation का जो amplitude है, that is called the input current in the language of transistors and amplifiers, etc. Okay. So make sure you understood this point over here. Now what happens as a result of that is that in this situation where there was no alternating input voltage connected, this would have generated a DC out collector current, which is beta times. So this would have been a DC current. But now in this situation, what is happening? Connected with the input signal connected across, IB is fluctuating. Okay, so IC will also fluctuate. So IC becomes beta times. So instead of the current remaining a constant flat line value, the input current is fluctuating with a comparatively small amplitude. But what will happen, because the output current, which is the current going through the collector, is beta, and beta is 50 to 200. So the amplitude also increases. So my collector current versus time, in the case of the DC thing, was looking like this. Okay, but this is the relation. But in the case of the AC now, with the input voltage connected, it's making the input current vary a little bit. So likewise, the current through the collector will also vary, but by a comparatively larger amplitude. Okay, so if you compare this collector current versus time with respect to the base current versus time, in this you will see that this will have a larger amplitude because of that factor of beta. So इसका जो amplitude है उसको हम output current बोलते हैं. So this is twice the amplitude of IC, or that is the current through the load resistor. That's why it's called the output. So this actually becomes 2 times I, where I output is not defined as the net current through the load resistor, but it is defined as the amplitude of the collector current, or amplitude of current through the load resistor. So just make a understanding of these two graphs and the circumstances in which they are achieved. Then we discuss further. So first of all, understand how your base current, which was constant before this input voltage signal was connected. This base current was a DC current driven only by this DC voltage source. Now that voltage is made to fluctuate a little bit, not between minus and plus, because obviously the DC one is dominating, but between a smaller value and a larger value. So what happens to the current also fluctuates. So your base current goes from a flat line value of capital IB to a fluctuating value of small ib. And the amplitude of this fluctuation is what we call the input, sorry, not voltage, but current. Just make a small correction here. So this peak to peak is 2 times V in, where V in, sorry, 2 times I in, my mistake again. This peak to peak is twice of I input, where I input is defined as amplitude of base current, or amplitude of current through the input source. Whatever input source is, small signal input source has been connected across the base emitter junction, उसके through जो current का amplitude है, that is called the input current, V or I in. Now the transistor makes sure that the collector current is a large factor times the base current. It is a large multiple of the base current. So if I make the base current start varying a little bit, like in the diagram above, so this is varying with a small amplitude. Now the collector current will start varying with a comparatively larger amplitude. And because the collector is where we've connected across the collector emitter junction, we've connected our external load. So whatever current is going through this external load, उसका जो amplitude है, वो मेरा क्या हो जाएगा? That will be my output current, or I output. So that is how I define I output. Okay. And next we'll see that the ratio of I output to I input is nothing but the current gain, and that will happen to be nothing but beta. Okay. Just make a note of this. Okay, so now let's understand the formula for the relationship between output current and input current. Okay, so we can see here that since collector current in the DC stage was equal to beta times base current, okay, this is with DC currents flowing. So this will hold true when the input voltage is connected across the base emitter junction. But note it is connected in such a way that this is a small signal voltage. So, and that to alternating voltage. So because it is small signal, it does not affect the biasing. So because it does not affect biasing, that is why this relationship holds and beta is constant. Okay. So from that we can say that if IC is equal to beta times IB, then any change in IC will also be equal to beta times the corresponding change in IB. Or we can say that the amplitude of IC will be equal to beta times the amplitude of IB. Now if you go back, the amplitude of that IC was nothing but the amplitude of the current going through the load resistor. So it was nothing but the what we defined as I output. It is the amplitude of the output current. And similarly, amplitude of IB was nothing but the amplitude of current that is drawn from the input voltage source. So it was nothing but I input. So that means my I output divided by I input, that is the ratio of amplitude of output to input current, or ratio of the amplitude of the current through the load divided by the current through the input source, is nothing but beta, and that is why beta is called the current gain. So the formula for current gain achieved through a bipolar junction transistor functioning as an amplifier is nothing but this. Where remember beta is actually determined by all the things, that is the physical form and design factor of the transistor as well as the biasing voltage is used. Okay people, so hope this is clear. Okay, now coming from current gain to voltage gain. So again, if we take a relook at that circuit diagram, understand the behavior of current in the circuit. So we have some resistor which we have connected across the base emitter junction. Then we have the small signal input voltage which we have connected between the input terminals, and of course there is this DC battery which is connected for the biasing, because we were using what is called an NPN transistor in common emitter configuration. So the emitter On the other side, we connected the load resistor across the collector emitter junction. So because this input voltage made your base current become a fluctuating current, it's no longer a DC value. So automatically your our collector current also becomes a time varying one, and so does our emitter current. So the current that is going through the load resistor we saw is now becoming a fluctuating quantity, and to that end we saw that delta IC by delta IB was equal to beta. So that is nothing but the amplitude of this current, which we are calling the I output, divided by the amplitude of this current drawn from the voltage source, which is I input, is becoming beta. That's what we've seen so far. Okay. Now next what we'll do is we'll apply KVL, Kirchhoff's voltage loop equation, to two loops. So one will be this loop. Let's say this loop 1, and next will be this loop. So let's say it is loop 2. So let's see those. So for loop 1, we have this minus whatever input voltage minus IB times RBE minus voltage across the base emitter junction is equal to 0. So the voltage across the DC battery plus the voltage drop across the input voltage source plus the voltage drop across the resistor here plus the voltage across the base emitter junction, and you're back to where you started. So the sum of these voltages is 0. Now if this voltage, the sum of these voltages is 0, then if we apply the formula of change, that is delta of the whole left hand side will be 0. In any cycle or any time period, if this is changed by a certain amount, the summation of this should be 0. Okay. But now notice that VVV is a constant term. It's a DC voltage. So what about delta of VVV? It has to be 0. And similarly, this term, the voltage across the base emitter junction, this is going to be constant, because why? The biasing has not changed. The presence of the input voltage source is not affecting the biasing because it's a small signal input voltage. So this is the voltage drop across the forward biased base emitter junction, and this does not vary with time, as long as the biasing is maintained. So that means the change in this quantity will also be 0. It remains constant. Typically, it is something of the order of 0.7 volts. Okay, so now apply that change formula in the above equation. So that delta of DC voltage, input voltage, input current into resistance RB, and base emitter junctions, this is 0. Now in that you have this factor that delta VB is 0 and delta VBB is also 0. So that means delta of V input minus delta of IB into R, this resistance, must be 0, because again the resistance is constant with time. Okay. So that means any change in the input voltage is the corresponding change in the base current into RB. Therefore, the amplitude of the input voltage will be equal to the amplitude of the current through the base resistor times RB, where this is the amplitude of the input voltage And of course, In we have seen earlier, it is the amplitude of the base current. So we have this relationship between input voltage and input current. So just go through this once and make sure you're clear with the steps. Okay, people. So hope this is clear. Okay, now similarly, if we consider the second loop on this side for loop 2, if we consider, so you see that it is just this thing. The voltage across the, or basically we have to consider the output voltage. So even that is not necessary. We don't need loop 2 actually. The voltage across the load resistor is only our output. And this is our output. So in loop 2, voltage across the load resistor, that is IC into RN. This is the voltage across the so-called output device, because the load resistor is the output device for the circuit. So this voltage will become IC, which was beta times IB times RL. So the change in VL at any point of time will be equal to beta times change in IB times RL. Because beta is a constant. Okay. Now, this will therefore become beta times because the amplitude of VL is nothing but the output voltage, and on the other side, the amplitude of IB is nothing but I input. So if I replace this delta VL with one full amplitude, is this much? And then correspondingly, the change in IB will become the amplitude of the input current at that point in time. So that is I input. So we can see that V output is beta RL times I input. And we had just seen that V input was equal to I input upon RB. That was from the above equation. Yes. Look at this equation. The input current's amplitude is nothing but the input voltage amplitude divided by RB. You substitute that over here. So you get that V output becomes beta times RL into I input, which is nothing but, this I have written the other way. This is into R. So this is this equation here. So the I input here I can replace with V input upon R. So from this we get the amplitude of the output voltage divided by the amplitude of the input voltage is the current gain factor beta into load upon RB. So this becomes the formula for voltage gain. So the value of voltage gain, that is the peak to peak amplitude of the output voltage, is to the peak to peak voltage of the, peak to peak amplitude of the input voltage. That ratio is nothing but the current gain beta multiplied by RL by RB. And one final formula you should know is power gain. So that is current gain factor multiplied by voltage gain factor. So that actually becomes beta square times the ratio of these resistances. So these are the important formulae for the amplifier circuit. This is the working principle for amplifier. So basically for your JEE mains level, the two important things here in terms of application is one is the biasing circuit for active mode biasing of bipolar junction transistor, and related to that the functioning as a transistor. So the importance of the parameter beta and the calculation of voltage gain and current gain and power gain. And the other important thing is the rectifier circuits using PN junctions as diodes that we had seen earlier. These are the two important things. Other than that, there is nothing asked in semiconductors mostly. very low weightage kind of chapter, all theory heavy. Alright, so just take a couple of 5-minute break or so, and then we'll discuss logic gates, which is the last part. So we'll understand this, though actually even this is very easy. But the main thing is we'll see how to implement logic gate circuits using semiconductor devices. Okay, people. So let's look at the last section of logic gates. So logic gates are basically they are circuits that implement logical functions, which eventually become Boolean or binary algebra. They implement these. So these are electrical circuits that are able to carry out calculations which are based on logical functions. So first we need to understand the basic logical functions and then their corresponding circuits. So there is the OR function, the AND function, and the NOT function. So logical variables, or you can also call them binary variables, are variables which have two values. The values is either true or false, or you can say yes or no, or in binary algebra it either becomes 1 or 0. So they have two particular values which in logical context can be thought of as true versus false, but in binary it can be thought of in terms of unity versus 0. Okay. So such type of variables are called logical variables, and any operations or any algebra involving logical or binary variables is called a logical function or a binary function. So as you know, the OR function it is such that if we say C is equal to A or B, it means that A is equal to true, B is equal to true, implies C is true. A is equal to true, B is equal to false, implies C is true. A is equal to false, but B is true, implies C is again true. So you see, logically why it is called OR, because at least if one or other of A and B is true, then C becomes true. And it is only in the special case where A is also false and B is also false that C also becomes false. In all other cases, okay. So this whole logical operation that we written in words, it is much simplified and it is written in what we know as the truth table when we write it in terms of binary. So every corresponding logical function like this one has a corresponding what we call a truth table. So the truth table for the OR function is like this. If C is equal to A or B, then A and B both being false or 0 will give you C as false. But any other situation will give you C as true. So this is called the truth table, which implements the same thing as the logical function that we've seen. So in future things in electronics and all, whatever more complicated logical functions and binary operations that we develop, they're always built as combinations of the three simple basic functions, which are AND, OR, and NOT. Okay. So similarly, when you look at the AND function, like this, that C is equal to A and B. This implies this kind of a truth table. I'm sure you've seen this so many times, you're well aware of it. But false false gives you false. If either one of them is false, also you get false. It is only in the situation where both A and B are true, that is A and B are true, then C is true. Any other situation, C becomes false. So these two are two of the very basic ones. The third one is the not, which we are coming to. So this is OR function, this is the AND function. I'll just have to restart my whiteboard program because it's giving me some errors. Just a moment. Okay, so these were the two basic functions, the and OR. Now, like that, we can see that there is the next function called the not function or the inversion function. So we see this complement symbol, B equals or B is not of A. Okay. Then the truth table for this, as you know, is very simple. If A is false, then B becomes true, and if A is true, then B becomes false. As simple as that. B is opposite of A. So that is the not function. Now there are some more functions which are combinations of these. So additional functions, they are the NOR function. They can be understood as not on. So this one's truth table becomes like this. Now remember, in OR function 0, 0 used to give us 0. So here it will give us 1. In OR function 0, 1 used to give us 1. So here it will give us 0. Because it is just the opposite of, it is not of OR. So this is the thing of not. Then similarly, another logic gate there is called the NAND function. Actually, first we are discussing about the functions. We'll come to the gates later. This is not AND. You just take the not the AND function and invert it. Function, you remember, this will give us 0 for this, so this will give us 1. This will give us 0 for this also, so this will give us 1. And only in the case where both A and B are positive or both A and B are true, then C becomes false. Okay, likewise we have one called the exclusive OR function. So this one's truth table looks like this. So this becomes 0, this also becomes 0. But when one of them is true and the other is false, C becomes true. This is the logical function called the XOR or exclusive OR function. Now coming to our main area of interest, logic gates. They are circuits that implement logical functions such that a variable is represented by a voltage. So E being 0 implies the voltage corresponding to that is low, and E being 1 corresponds to the voltage related to the variable A being high. So now it becomes from an algebra of zeros and ones or binary, or from a logical function of true and false variables, to an electrical circuit where the voltage at different points, which represent the different voltages, is alternating between high and low. So let us see how this implementation works. So for example, let us see a particular logic gate which we can achieve by implementing something like this. Okay, so this is any voltage cell. This is any kind of resistor. Now this we want to understand, suppose for this we want to determine the truth table for this logic gate where A and B are input variables and C is output. Okay. And these are diodes. D1 and D2 are semiconductor diodes. Just try to work this out. Try to understand how this will implement digital logic and what is the situation we're giving. Can anyone tell me which standard logic gate this is? There's some standard logic gate circuit, one of the 3 standard logical functions that we studied. Not the extended ones, but one of the standard ones, one of the basic ones. Which one does this implement? नहीं बेटा मनीष का not नहीं होगा because not is a 2 variable function ना, like B is not of A like that. This is a 3 variable function. C is the output variable for A and B being input variables. So it is either one of and or. Now just try to understand which one of them it is. Okay. You realize that this is one of those 2 basic ones, and or. Now just to understand, so make a truth table where you connect each case. So for example, if you take the case where A and B are both 0, that means you have to ground both the pins A and B. So see what happens when you ground the pins A and B, and how much will be the voltage of C. Similarly, suppose you're taking the case where A is 1 and B is 0. That means you're connecting A to a high voltage, but B is grounded. So then see what kind of voltage you get at C, and accordingly, you can understand how it's fulfilling the truth table, and from that you will understand. So just try this out. Yeah, so people will understand this actually implements. Let's see. Okay, so what happens, for example, if I connect both A and B to high voltage? If I do this, so क्या हो रहा है? This is also reverse biased because this side is high voltage. This is also reverse biased. So there is no current that flows. So ये current भी zero है, ये current भी zero है. So ये वाला current भी zero हो जाएगा. So voltage of the point C will become plus E. So that is high. Okay. So that is telling me that when A and B are high voltage, then if VA is equal to a high voltage, VB is also equal to a high voltage. At that point of time, what is happening? VC is becoming a high voltage. That means A is equal to 1, B is equal to 1, implies C is equal to 1. Okay. Understood this? Okay. Now next, let's see if I make one of them low voltage or ground or something like that. Okay. So next stage, what I do here is instead A is made low or it is connected to ground. So VA is low. So now what happens? This becomes forward biased. The moment this becomes forward biased, there will be a current that flows. So this is forward bias. So there will be some current I1 going through this, which will be equal to this current I. And instead of this, the voltage of C will become E minus IR, which will become a low voltage. So this is what is now happening. For VA being low or ground, BB being high, what is happening? I1 is equal to I, and VC is equal to E minus IR, which is low. So this is giving me that A is equal to 0, P is equal to 1. Okay. Similarly, if I had VA as high, but VB as ground, that would correspond to I2 becoming equal to I, and I1 would be 0. Here the current in the second diode is 0, but the current in the first diode is the current here, and that would implement the same thing, that VC is E minus IR, so it is low. So this would correspond to A being 1 but B being 0, giving us the value C still as 0. Okay. So this is implementing, as you can see, the AND gate. And likewise, if both are grounded, then both the diodes are conducting. So the current I becomes I1 plus I2. So again, the voltage of C becomes low. So if BA is also ground, BB is also ground, then I1 is not 0, I2 is not 0, and I is equal to I1 plus I2. So VC again becomes low potential. So A is equal to 0, B is equal to 0, also corresponds to C equal to 0. So it implements what we call the AND gate. Right, so hope this thing is fully clear. So in digital circuits, because we implement very large number of such logical gates, so we develop short forms for each one. So that whole gate that consisted of the two diodes, the resistor and the cell, that is now drawn as a short symbol like this. This is the circuit symbol for AND gate. This symbol corresponds to that truth table. Similarly, we use this symbol for the OR gate. And as a circuit inside the OR gate, what is implemented is the digital logic, which is shown by this particular circuit diagram I'm making now. So you see that this implements the OR gate, because in this, at least one of the two diodes is forward biased. So VB is high. So this is forward biased. So there is a current through this. So there is a current through this. And the voltage of C becomes IR, it becomes high. Suppose this is grounded. So this is reverse biased. So I1 is 0. There is no current in this, but still there is this I. So VA is ground, VB is high, corresponds to I2 equal to I, non-zero, and I1 0. So voltage of the point C becomes. Similarly, VA was high and VB was ground would give you again some current. Both VA and VB are high would give you some current, but only in the case where both A and B are grounded. In that case, there will be no current. If VA is 0 and VB is 0, then I1 is equal to I2 equal to 0. So current I is 0. So voltage of C also becomes 0. So this is the only case where VC becomes 0. All other cases, VC is the high voltage because there's some current in that resistor R. So that is why this implements the OR kind of logic. Okay. And this whole circuit in short form is made in digital circuit diagrams as this particular diagram. And finally, you have the NOT gate, which is given by this kind of a symbol, a triangle. So B is not of E. So this implements this. Okay. Now let's see how this exactly implements. So this is the only one which involves a transistor. Now in this circuit, this terminal is V. This terminal is V. So here you can see the moment to connect VA to a high voltage, what happens is that the base emitter junction it becomes forward biased. So the resistor R experiences, so the moment we connect this to a high voltage, this happens. There is base current, there is collector current. So forward bias means collector current is large. So you can see that the voltage of the point D becomes VCC minus IC into R, and current is a large value, so this becomes a low voltage. So E being a high voltage gives you B as a low voltage. Then on the other hand, if you ground A, then it is not biased. The base emitter junction is not biased at all. So there is no base current, so there is no collector current. Because remember, collector current was beta times base current. So on the other hand, if E is grounded, so it's at low voltage. So the base emitter junction is unbiased. Okay. So collector current is 0. So what about the voltage of that point D on that side? It just becomes plus VCC or high voltage. So E being grounded corresponds to D being at a high voltage. So just leaving you for a moment with the circuit diagram. So this is how we implement the 3 basic gates: the AND gate, the OR gate, and the NOT gate. The NOT gate using a transistor, the AND and OR gate using a combination of 2 diodes with other things. And all other logic gates which are more complicated, like the XOR or all these other ones, they are just combinations of this. Okay. So all this is given in reasonable detail in HC Verma. Not as much lengthy detail like there is in NCRT. Just a moment, people. But just enough that you require JEE means. HC Verma part 2 is a good sort of theory collection thing to revise this part, semiconductors and logic gates. Don't get into NCRT, not for JEE means, it is too lengthy. Unnecessarily you will have to read a lot of extra things and waste your time. Okay, so for example, now using these basic gates, if you want to implement something like the NOR gate, all you do is you take an OR gate, input A and B into this, and the output of the OR gate is now put through a NOT gate. This now gives. So for example, if we had E equal to 1 and B equal to 0, this would over here become 1 or 0, which is equal to 1. But then this would become not of 1, that would become 0. So C would become 0. Okay. Similarly, for example, if we had E equal to 1, B equal to 1, so same thing, C would also become 0. But if we had E equal to 0 and B equal to 0, then over here we would have 0. So E or B will become 0. So not of A or B. So this is how we, a logic gate consists of layers. First an OR gate and then a NOT gate, implemented in series combination so that it gives you that logic of NOR. Okay. Similarly, if you put a NOT gate in front of an AND gate, it becomes a NAND gate. So the NAND gate is like this. In front of the AND gate, you put a NOT gate. So this is the output variable C. And these are your input variables. So C is equal to Amen. And the exclusive OR is a very interesting one. The exclusive OR is actually broken down like this. So you can see that this input here is A, but this is B complement. So this is giving us A or B complement. Similarly, this is A complement. This is B. So this is giving us A complement or B. And finally, this is an AND gate. So this is giving us A or B complement and with A complement or B, which is the value of C. So you will see that this actually implements exclusive OR. Okay. Let's understand how this implements exclusive OR. We got A, we got B, and then we got A complement or B, A or B complement, and then we got that C variable, which is the AND of these two. Okay? So if both of these are 0, then this becomes 1 because A complement is 1, so 1 or 0 is 1, and this also becomes 1, and AND of these two becomes 1. But for example, if this is 0 and this is 1, okay, then what happens? A complement or B becomes 1, but A or B complement becomes 0. So their AND becomes 0. Similarly, if this is 1 and this is 0, then A complement or B becomes 1, but A or B complement, becomes 0. Because both of these are 0. A complement is also 0, B is also 0. Whereas A or B complement is 1 or 1, which is 1. So these two AND becomes 0. Because remember, C was A complement or B and with A or B complement. It is the AND of the earlier two tables. And finally, if this is 1 and this is 1, then what happens here? This is also 1 because this becomes A complement, which is 0, or B, which is 1. So 0 or 1 is 1. This becomes 1 or 0, which is also 1, and 1 and 1 becomes 1. So this is the exclusive OR function. So the exclusive OR function can be implemented using a chain of logic gates like this. So this is the part of logic gates which you have to know. Okay. So that completes the semiconductor and logic gates part. Again, because it's JEE mains and this portion really doesn't have anything much to do with application difficulty type of questions. It's either direct application questions like the logic gate circuits, or just a few theory questions here and there about PN junction and biasing and all that. or just direct formula based on alpha beta parameters and voltage gain and all that. So if you just go through my notes and just last 4-5 years questions from JEE mains, it should be more than sufficient for your purpose. That's it for today, guys. Okay, thank you. And any doubts you have regarding this or anything else, you can just share with me on WhatsApp. I'll get back to you.